In this work, we present GAN Cocktail, a new way for mixing GANs without dataset access. The problem formulation is the following. Given several pre-trained GANs, for example, GAN that generate dogs while the other one generate cats, we aim to find a unified model that can generate images from all the classes using a shared latent space. This model mixing is well suited for decentralized workflows. Many different entities can collect their own datasets and train their own models, which may be later combined together. In addition, merged models can reduce memory and computation requirements, enabling their use on edge devices with limited computational resources. Furthermore, using merged models can perform semantic editing across domains, as we will see later. We constrain our possible solution to those that assume no access to the training data, because many of the publicly available models do not include their training data. In addition, we assume limited computing power, so simply keeping all the pre-trained models is not possible, because the model size would grow linearly, and there will be no shared latent space that can be utilized for semantic editing. We propose a two-stage approach. At the first stage, we perform model routing, and in the second stage, we perform model merging. In order to use the weights of the two pre-trained models, we need first that the models will have the same architecture, and second, that the weights belong to the same semantic space, such that the same semantic directions operate on both of them in the same manner. Assuming we have two pre-trained GAN models with the same architecture that were trained on different datasets. If we simply average the weights of the models, the output results are meaningless. Exponential weights average is a technique for averaging the model weights during the training process in order to merge several versions of the same model from different checkpoints during the training process, which can be seen as an ensemble. A key feature in exponential weights average is that averaging is performed on the same model from different training stages. Thus, we can say that averaging is done on models that share the same common ancestor model. Taking inspiration from exponential weights average, we choose one of our models to be the root model, and then fine-tune this model for each of the other datasets, yielding n rooted models. Importantly, these models now share a same common ancestor. As we can see on the right, mixing the rooted models produces results that are semantically more meaningful. On the second stage, we create an average model by simply averaging the model's weights, and then fine-tune the average model using the original model's outputs. This gives us our final model, which can produce images from the domains of all the input models. We tested our approach under different number of datasets and datasets types, and showed that our method outperforms the baselines in terms of FID score. Using our method, we can perform latent space interpolations between images of different classes. We can also do style mixing between images of different classes by taking the appearance from the cat's dataset and the pose from the dog's dataset. Finally, we can calculate semantic direction on one of the classes using a classifier. For example, the human head pose, which is easily acquired by an off-the-shelf classifier, and apply it to the other class, cats in our example, where such a classifier is not available. This method also works on other directions, such as human's glasses direction, that is being translated to the cat's eyes size direction. For more details, please read our paper. Code is available on our project page.